In 1977, NASA is given an enormous challenge: build a space telescope with the potential to unlock the secrets of our universe.
It's an engineering wonder. It really is an engineering miracle.
The project pushes engineers, scientists, and astronauts into uncharted territory.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
We put our careers and our lives in that shuttle bay.
From construction to release.
Solar panels wouldn't go out. They were stuck.
I need answers now.
From ridicule.
I thought that there was no conceivable way that they could fix this.
To redemption.
Man, that was a neat moment.
It's a classic story of human ingenuity and human perseverance.
This is the story of the unsung heroes who built the Hubble Space Telescope.
Discovery, Hubble is open for business.
December the 7th, 1993. In the lethal environment of space, astronauts risk their lives trying to save the $1.5 billion Hubble telescope.
We had to do it. The future of Hubble was at stake, perhaps even the future of our agency.
The servicing mission was a technical challenge like none anybody had ever seen.
Delicate new hardware must be installed. Without it, the telescope's performance is critically impaired.
You've got this huge spacesuit on with big, thick gloves. How in the world are you going to do very fine electronic work?
You check your mechanisms, cot restore?
People considered that to be the most critical maneuver. If I tap that thing, it's over.
Okay, are you ready for me to let go? Yes, I am.
For over 2 decades, the Hubble Space Telescope has provided humanity with unparalleled views of the universe.
Hubble isn't just a satellite. It's about humanity's quest for knowledge.
Before it, images of this clarity simply didn't exist.
Hubble shows us the beauty of the universe. We all can look up at the sky at night and wonder what's going on out there. Where did we come from? Who are we? Is there anyone else out there? And Hubble helps us to come up with the answers and shows us the absolute beauty of what's out there.
The great fun of science is that it answers questions and that it creates questions, and Hubble's done both.
Named after American cosmologist Edwin Hubble, this school bus-sized observatory circles our planet at over 25,000 kilometers per hour, capturing light 6 billion times fainter than the human eye can see.
Your eye can see more or less a flashlight, a 2-cell flashlight, maybe a couple miles. Hubble could see that flashlight on the moon, 240,000 miles away.
Just keeping the proposed telescope steady enough to take photographs in space demands unprecedented engineering.
Hubble had to be stable with an angular precision of 7/1000ths of an arcsecond. This would be analogous to putting a laser on top of the Washington Monument in Washington, D.C. and illuminating an object the size of an ordinary 10-millimeter pearl at a distance of New York City and never going off that diameter of that pearl for 24 hours at a time. This is hard, folks.
The incredible journey to build this revolutionary machine begins over 70 years ago. September 1946. American astrophysicist Lyman Spitzer writes a short paper that changes the course of history. He's frustrated with trying to observe space from the Earth's surface because our atmosphere blurs the view of the heavens.
You know that Twinkle, Twinkle, Little Star? Well, everybody loves that song. Astronomers hate it because they want to get rid of that twinkle.
Earth's atmosphere also filters out wavelengths of light such as ultraviolet that are critical for unraveling the evolution of our cosmos. Inspired by advances in rocket technology, Spitzer makes a revolutionary proposal: an orbiting observatory above our atmosphere.
The idea of putting a telescope in space, I mean, give me a break. We didn't even have satellites when Dr. Spitzer wrote that paper.
Spitzer devotes the next 3 decades to promoting cutting-edge research which will make his dream possible.
What Lyman Spitzer did is move the space telescope idea from pure science fiction to you might actually be able to do this.
In 1977, his efforts are finally rewarded when Congress approves funding for a space telescope. NASA must now deliver Spitzer's dream. But building this telescope is an immense technical challenge. Chief Engineer Jean Olivier shoulders much of the burden.
Hubble was an extremely ambitious program. The further we got into it, the more ambitious we realized it really was.
Before construction of the telescope can even begin, NASA must decide how to launch it into orbit. As it happens, the agency's crown jewel, the Space Shuttle, is in the final stages of testing.
As NASA put all of its dimes into the Space Shuttle, many scientific missions had to be redefined in terms of being carried by the shuttle.
Fitting into the shuttle's cargo bay, the telescope will be latched to a tilting mechanism.
Putting Hubble into orbit with a reusable vehicle offers engineers a fantastic new opportunity.
The Space Shuttle was going to be there to service the Hubble and upgrade its instruments every 3 years or so.
To ensure Hubble can be improved over time, engineers design it to be modular. Each of its 5 scientific instruments, tasked with unlocking the mysteries of the universe, must be packaged in its own easy-to-replace box.
And so everything had to be done such that it can be removed, but removed by spacewalking astronauts.
But while using the shuttle extends Hubble's shelf life, it has one major drawback.
Basically, Hubble was built as large as it could be built to fit in the shuttle bay. I'm sure many of the engineers wish they had more room, as it turned out.
Hubble needs to be smaller and lighter than Earth-based telescopes, but also have more advanced scientific capabilities. And no instrument is more important to the tax-paying public, whose dollars fund the project, than the one that will provide the pictures.
If you had asked, what's the one thing that you have to have? The answer is you had to have a camera. But at the time, nobody had built a camera that had to be this good.
Unlike most telescopes on Earth at the time, it's not practical for Hubble's camera to use photographic film.
We had to have a camera that would work very remotely and send a signal back.
Restricted by size, the camera must be lightweight, robust, and sensitive to a wide spectrum of light. The battle comes down to 2 very different devices.
You had a choice that had been tested, the television-type camera tube. But then you had something new, something untested, but really promising, and that is solid-state silicon technologies that we call today charge-coupled devices.
These nifty electronic eyes convert light into electricity, building up a picture made of tiny individual squares called pixels. Smaller and more sensitive to light, the charge-coupled device, or CCD, appears to be the better bet. But there are serious drawbacks. They're untested, can't detect UV light, and they have a field of view much smaller than the television-type tubes.
It was pushing the state-of-the-art a little bit too far, a lot of people thought.
With no clear winner, NASA puts out a request for proposals. Bob Odell is a prominent member of the selection committee.
I cannot say I made the selection, but I wouldn't have been in the room without having a strong opinion and expressing it.
At the California Institute of Technology, the challenge attracts the attention of two maverick professors, Jim Westfall and Jim Gunn.
Jim Westfall was wonderfully hands-on. He was absolutely a Thomas Edison-type person. Jim Gunn was the scientist, well acknowledged to be one of the smartest guys in our field.
Since 1975, they've been experimenting with ground-based telescopes fitted with CCDs.
They were clearly the magic bullet, so we had to do this.
Autumn 1976. James Westfall agrees to lead the project and recruits an elite Caltech team to help engineer the world's most sophisticated camera. They begin fresh experiments with the technology they hope will form the core of the camera: charge-coupled devices.
You have a thing that's very, very close to this in your smartphone. The problem was that at the time this technology was very new, and though it was incredibly promising, it was also very risky.
Convincing NASA that CCDs are the technology to go for means overcoming some critical engineering challenges. First up, field of view. In the mid-1970s, CCDs are relatively small. This limits the size of image they can produce. But scientists demand that Hubble's camera has a wide field of view to record larger portions of the cosmos. To compete with television-style cameras, Westfall must increase the CCD's field of view by at least a factor of 4. As it happens, Bob Odell has a radical solution that he chooses to share with Westfall. Instead of building a single, larger CCD, he suggests using 4 smaller ones. As light from the telescope enters the camera, a specially designed pyramid-shaped mirror splits the beam and redirects it onto 4 separate CCDs.
So the final image is a mosaic of the 4 components.
Now just one daunting engineering roadblock stands in Westfall's way: capturing ultraviolet light.
People are very interested in what stars are made out of. They're very interested in what the gas in the galaxy is made out of. To understand that, you really need to look into the ultraviolet.
The trouble is, CCDs can't see in the ultraviolet spectrum because the silicon they're housed in absorbs it. Westfall must overcome this crucial problem.
Problems were something that Jim solved. So naturally, he was the guy who was going to do this.
For inspiration, Westfall turns to nature. He studies chemical reactions that occur in living organisms which create light. Through his research, Westfall unearths some potentially game-changing chemicals that can convert UV light into visible light through a process called fluorescence. To test if fluorescence can be recorded by CCDs, Westfall carries out top-secret experiments with 2 different chemicals. Each is given a code name to ward off competition.
They'd talk about it as bug juice or mouse milk, this kind of magical stuff that you put on the surface of the CCD.
Westfall coats the CCDs in either bug juice, the chemical lumogen, or mouse milk, the chemical coronine, by evaporating them in a vacuum.
Nobody had done that kind of thing before with these devices.
Next, the detectors are inserted into a camera, exposed to a UV light pattern, and a picture is taken. If the tests fail, Westfall and Gunn's dream to build the Hubble camera is over. The results with coronine are a breakthrough. The 2 main barriers to using CCD technology have now been overcome. Westfall's team have increased the detector's field of view and discovered how to record ultraviolet light.
We were able to convince NASA that this was a technology that worked, but mouse milk won over bug juice in the end. So.
NASA greenlights construction of Westphal's wide-field planetary camera, known as JD'ASYFK, with its core technology of CCD detectors. For the public, the camera will define Hubble's success.
We had to do great science, but also get that science to the public. So pictures were critical. And what instrument produced the neatest pictures? The wide-field planetary camera.
NASA's chief scientist, Ed Weiler, pushes for the construction of a duplicate camera to keep in reserve.
Having an insurance policy that would only cost maybe $50 million was worth it.
After some cajoling, the NASA hierarchy approves the idea, and the following year, work starts on a replica camera, JD'ASYFK 2. Crucial to the success of all Hubble's instruments is the design of the telescope itself. Telescopes capture light using lenses and mirrors. The bigger they are, the more light they can gather, and the more detail they can see. The further the light travels inside the telescope before it's focused, the greater the magnification. But because Hubble must squeeze into the bay of the space shuttle, it can't be as big as engineers would like. To extend Hubble's view into the universe, they boost its magnifying powers using a 300-year-old optical trick, hyperbolic curved mirrors. Reflecting light back and forth inside the telescope increases the distance it travels, making the instrument more powerful. It's the perfect solution to engineering a lightweight, high-performance telescope. But the success of this design hangs on the quality of the telescope's light-gathering primary mirror.
It's the brain or the heart of the telescope. That's where it all starts.
NASA contracts the Perkin-Elmer Company to undertake much of the complex technical work. This includes engineering the mirror.
The most challenging thing first was to build a mirror precisely enough to meet the resolution needs.
It had to be accurate over that 2.4 meter surface to a millionth of an inch.
If you were to take the diameter of Hubble and blow it up to the size of the Earth, then any deviation of more than about 6 inches would be unacceptable.
To achieve this level of precision, Hubble's primary mirror is carved from a 1-ton block of glass and meticulously polished with a spinning abrasive pad controlled by computers. After polishing sessions lasting up to 70 hours, the mirror's shape is analyzed in this chamber.
The task of the optician to make the Hubble mirror is first to create a device that allows him to measure the surface.
But creating equipment that can measure accurately enough is a challenge in itself.
With Hubble, we wanted to make a perfect mirror. And so the Perkin-Elmer, really smart guys, conceived of a thing called a reflective null corrector.
A null corrector is a precision optical test device. By shining a beam of light through this carefully calibrated instrument, engineers can create a light wave pattern in the exact shape of the desired mirror. This light is then reflected back by the mirror and the interference pattern recorded. Straight strips mean the mirror's curvature is perfect. A distorted pattern indicates it's the wrong shape. By studying these images, optical engineers know where to continue polishing the mirror to create the perfect curvature.
The null correction test is accepted as one of the most precise methods of testing.
But it's a painstakingly slow process that puts Perkin-Elmer badly behind schedule.
I think originally it was supposed to take 9 months and probably took twice that.
As preparations for launch begin, Perkin-Elmer deliver the mirror to NASA. What they don't realize is that a tiny flaw in the test equipment has gone unnoticed.
It was an oversight, and it had enormous ramifications in the life of the Hubble Space Telescope.
3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
January 1986, just months before Hubble is due to launch.
Challenger, go at throttle up.
Roger, go at throttle up. God, no.
The Challenger disaster plunges the space shuttle program into turmoil.
Obviously a major malfunction. Okay, everybody, stay off the telephones. Make sure you maintain all your data. Start pulling it together.
As America comes to terms with the tragedy, NASA grounds the shuttle fleet, and Hubble's launch is postponed indefinitely. For 4 years, it sits in hibernation.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Finally, on April the 24th, 1990, after 13 years of blood, sweat, and tears, Hubble is ready to leave Earth.
By the time we launched, about 10,000 people had spent some part of their lives working on Hubble.
Roger roll, Discovery.
And you realize that sitting up there on the very top of that pillar of fire is this thing that you have attached your life to. This thing that is carrying the hopes of a whole science.
Discovery's velocity now 2,300 feet per second.
It kind of takes your breath away.
Discovery soars to over 600 kilometers, higher than any shuttle has flown before, to place Hubble above the Earth's atmosphere. Now it is time to set the telescope free.
Discovery, your go to transfer Hubble to internal power on time.
Roger that, understand. Go for transfer to internal power on time.
Story Musgrave is capsule communicator at Mission Control.
I knew the importance of that mission. I knew what Hubble meant to people.
To generate power, Hubble relies on 2 solar arrays, absorbing energy from the sun. But to unfurl the arrays, there is a critical stage where Hubble must run on internal batteries. NASA must deploy the solar panels before the batteries run down.
Once you've taken the power off of Hubble, it's going to die. So we're time constrained.
The first panel unrolls perfectly. Now, time for the second.
Houston, Discovery, it looks like motion stopped with just about 1 panel showing.
They're supposed to motor out, and it wouldn't go out.
It's like you're watching the birth of your baby and it's stuck. It's a big deal.
Okay, with the panels that you got out there right now, it's not satisfactory to stay overnight.
Years of work and billions of dollars are at stake. Engineers must find a way to release the stuck panel before time runs out.
I need answers now.
The problem is quickly diagnosed.
Discovery, go ahead.
We think there may be some problem with the tension monitoring software.
A sensor is saying tension in the panel is too high. One solution is to override it. But this could snap the solar array's stem booms, rendering them useless. It's risky, and engineers are split.
We need to get on with it.
Under pressure from flight control, Jean Olivier is in the hot seat.
Finally, it became clear we were at a deadlock, so I just had to say, no, we're going to do it. We're going to override it.
We are disabling the tension check.
Okay, Houston, we see motion.
It's fully deployed.
You let the breath go out, you let the air... Okay, we got through that one.
Now receiving the full power of the sun, Hubble can finally fulfill its primary purpose: to capture the universe in unprecedented detail.
In Discovery, Hubble is open for business.
We got our telescope.
We got our telescope.
That's it.
Good luck, Bill.
May the 20th, 1990. Scientists and engineers eagerly await the telescope's first image.
The first image comes down, and it doesn't look at all like what we expected it to. Not these sharp little images, but instead were kind of these big blobs that frankly didn't look any better than the ground-based image.
Something has gone drastically wrong with the $1.5 billion space telescope. But what? June 1990. Over the next month, every effort is made to understand what's causing Hubble's blurred vision.
It was a puzzle, a very dark puzzle.
Part of the JD'ASYFK camera team, John Holtzman and Sandy Faber, analyzed 6 further images taken by the telescope. They hint at a catastrophic problem: spherical aberration. Spherical aberration is caused when the primary mirror is built the wrong shape, so that it fails to focus light into a single point. Instead, light is smeared out and the object appears blurred. It's such an unlikely mistake that many engineers and scientists can't believe it's true.
I don't think any of them would have predicted that something as basic as the curve on the mirror would be wrong.
We're sure that spherical aberration isn't going to be a problem. You know, nobody's going to screw it up that badly.
But Holtzman and Faber have compelling evidence that supports the theory. Holtzman shows the NASA hierarchy a comparison of 6 photographs taken by the telescope with a series of 6 computer-simulated images with spherical aberration built in.
And the match was nearly perfect, and I think that kind of proved to everyone that that was the problem that we had.
The most accurate mirror ever made is flawed.
It was made very accurately, very beautifully to the wrong prescription.
In July 1990, an inquiry into the cause of Hubble's faulty mirror reveals a mistake with the test equipment, the null corrector.
It wasn't quite aligned correctly, and that built into the whole operation an aberration.
Misspacing the null corrector by only 1.3 millimeters, the outer edge of the mirror was polished incorrectly by 1/50th the diameter of a human hair.
We very precisely did the wrong thing.
The management error was that there was not enough checks and balances.
Now we'll open the floor for questions.
Of Hubble's 5 scientific instruments, the wide-field planetary camera is the worst affected. It's a major blow for everyone involved with the telescope.
It would be dishonest of me to say this, the mood of the scientist is very happy right now. We're all frustrated, obviously.
If you ever want a picture of a person just in anguish, go and find a picture of Ed Weiler at the end of that press conference.
We feel right now that there's probably no real science that we can do with the wide-field camera at this time. And I'll stop there. It was very depressing, because a lot of us have put our lives into this our entire careers. Clearly, Hubble's future was in doubt. Perhaps the space shuttle's future was in doubt. Perhaps NASA's future was in doubt.
Some of the founding fathers are so disillusioned, they leave the project altogether.
About this time, I didn't have enough faith in NASA. I thought that there was no conceivable way that they could fix this.
The press have a field day at NASA's expense.
God, they were vicious. One that I remember, Jay Leno, he just hit it again and again and again. And one of the jokes that I remember, it was around Thanksgiving, and he said, what sound does a space turkey make? Hubble, Hubble, Hubble.
As public support for Hubble dwindles, it appears the dream for this space telescope is over. But Charlie Pellerin, the man in charge of the Hubble program, refuses to give up hope.
This was a horrible, deep pain, and only one way to get rid of it, and that's to find a way to fix the telescope. There was no other way.
The burning question is how to correct the flaw. Pellerin risks his career by secretly bankrolling a mission to find an engineering solution.
So I brought in my budget analyst, and I said, I want to find $60 million. And by the way, you can't tell anybody we're doing this.
The fact Hubble can be serviced by astronauts offers a glimmer of hope.
If there were no way to service the Hubble, Hubble would have rapidly become, in 1990, a very expensive piece of floating space garbage.
It's only now that Ed Weiler's decision to build a backup camera becomes a masterstroke.
And thank goodness we had that clone ready to go, because it was a simple fix to change out 4 little nickel-sized mirrors.
These mirrors divert the light from the telescope to multiple electronic detectors within the camera.
It was like going to the optician and saying, well, your eyes aren't quite right. You need this corrective lens. We put that correction on those little mirrors.
It's an internal fix that can be done by engineers on Earth. When it's installed, the new modified backup camera will go some way to fixing Hubble's vision. But saving the 4 other instruments that scientists hope will unravel the mysteries of our universe proves much more challenging.
The other instruments didn't have clones being built to them. There were no second copies.
These instruments require an external fix that can only be done by astronauts in space. The goal is to place corrective mirrors deep inside Hubble, in front of the remaining instruments, to correct their vision. But squeezing them into a very restricted space proves a technical nightmare. Jim Crocker is part of a multinational team tasked with finding a solution.
There were literally hundreds of ideas, but all of these were either impractical because an astronaut couldn't do them in gloved hands, or because it was too dangerous, such as going down the barrel of the telescope where an astronaut might be trapped.
A mechanical fix is needed that won't put the astronauts at risk. But the team struggles to come up with a viable design. After a conference in Germany, Crocker returns to his hotel.
I went to take a shower, and when the maid was cleaning the room, she had folded the arm down and slid it all the way down to the bottom. So to take a shower, I had to slide it up and raise the arm. When I did that, I had this epiphany. The shower head got me into a different way of thinking. So it was the idea of raising something up above the other instruments and flipping it out to do the correction that we hadn't thought of before.
In this moment, a corrective optics device, CoStar, is born. It will be pre-packaged in an astronaut-friendly box with mirrors that deploy remotely. The only downside, one of the existing scientific instruments will have to be sacrificed to make room for it. Crocker's showerhead-inspired invention is now displayed here at the Smithsonian's National Air and Space Museum.
This is the elegant engineering solution to what was a daunting technical challenge. The little mirrors that you see were deformed precisely to counteract the flaw in the main mirror. And only once the entire box was inserted, with everything protected inside, did the column extend, and then as it extended, deployed these little stalks with the mirrors into the optical beam of the other instruments.
To repair Hubble, both WIFPIC 2 and CoStar must be installed by astronauts on a series of grueling spacewalks. This takes 3 years of meticulous planning.
Stop, stop, up, up.
Story Musgrave who's been working with Hubble for 15 years, is the first astronaut to be recruited. To prepare his body for the spacewalking ordeal ahead, Musgrave goes to extraordinary lengths, enlisting the help of Olympic athletes like figure skater Dorothy Hamill.
I brought athleticism into the spacewalking world. If you look at a spacewalk, it is the choreography, the dance of this body and the tools that's going to get to the finish line, and that's it. There's nothing else. That's it.
As expectations of rescuing Hubble grow, the mission becomes more than just repairing a telescope.
It wasn't just Space Telescope that was on the line. It wasn't even NASA that was on the line. It was the broader question of, do we still do big science? If the servicing mission had failed, that may well have been the end of trying to do things like this. And we knew it.
We just had to do it and do it right.
30, SLB ignition.
December the 2nd, 1993, Kennedy Space Center.
Roger roll, Endeavour.
Space Shuttle Endeavour thunders skywards on a mission to rescue Hubble.
We put our careers and our lives in that shuttle bay.
It's quite a sight.
As Endeavour approaches Hubble, the crew reaches out with the robotic arm to capture the telescope.
Houston, Endeavour has a firm handshake with Mr. Hubble's telescope.
We copy that, Cubby, and there are smiles galore down here.
With Hubble tethered, the astronauts embark on a series of perilous spacewalks.
People are willing to put that suit on and go out there and try and fix a science instrument is heroism at a level that almost unparalleled.
After 2 days of intricate repairs, Story Musgrave and Jeff Hoffman removed the original wide-field planetary camera in order to install the backup, WIFPIC 2.
Okay. You check your mechanisms cocked, Story? I just cocked them, yes. I pushed on them.
At the front of the unit is a delicate instrument that diverts light from the telescope into the camera, the pick-off mirror.
This was the most critical part of 40 hours of spacewalking. If I touch that mirror, it's over.
As the world watches, Musgrave and Hoffman slowly maneuver the WIFPIC 2 camera into position.
These astronauts have to take this thing and somehow manage to slide it into this bay.
Looks like it's in there. Well, okay. Are you ready for me to let go? Yes, I have it.
The camera is installed without a hitch. Now for the corrective optics device.
Keep coming up, coming up, coming up.
Pre-packaged in a module the size of a telephone booth, the device is key to every other instrument on Hubble working perfectly.
The booth just went in, bang, put the power tool on, it's done.
The crew of Endeavour complete one of the most ambitious repair missions in the history of space exploration.
Through your superb efforts, you have really shown that NASA can do all that we promised to do and more.
Good job. That's great. Congratulations.
Thank you.
Joe.
But has Hubble's eye surgery been successful? 4 days after Endeavour's triumphant return to Earth, Hubble's new camera transmits its first image. It's the moment of truth for those who've dedicated their lives to the telescope.
And the image comes down, and here it is coming up on the display. And it was right. I mean, how do you describe that? How do you capture the emotions when you've been a part of something that was built up with such incredible high hopes? Man, that was a neat moment. God, that was a neat moment.
And then having that first picture come down and prove, and absolutely prove, that we had fixed the Hubble Space Telescope. That was a moment of redemption.
Get it!
I said, holy and I wasn't fired for it.
Over the next quarter of a century, Hubble observes more than 30,000 objects and beams back over 500,000 images. Its discoveries transform modern astronomy.
And you think about it and you're looking 10 billion years back, and you're seeing history in front of your eyes as the light comes. And it's an amazing thing.
Witnessing the birth and death of stars, confirming the existence of supermassive black holes and thousands of unknown galaxies, and measuring the age of the universe, Hubble's science and images transfix the world. Between 1993 and 2009, 4 further shuttle missions returned to upgrade Hubble. Aboard 2 of those is astronaut Mike Massimino.
Okay, Mass, you have a go.
There we go. I think it's the greatest scientific instrument ever built, not only because of the science it produces, but because of the engineering that went into it.
What a beautiful view.
It's an engineering wonder. It really is an engineering miracle.
But after a quarter of a century in orbit, and with no more servicing missions planned, Hubble's days are numbered.
And we wish Hubble the very best.
Now, there's a new kid on the block. Set for launch in 2018, the James Webb Space Telescope will extend our window into the universe.
We're going to see unprecedented views of the birth of stars and planets, the origins of life.
As with Hubble, engineers work tirelessly behind the scenes to ensure the mission's success.
The thing that keeps me up at night is the problem we didn't think of, so-called failure of imagination.
While the James Webb Telescope is the future, Hubble's engineering tribulations and eventual triumph ensure it a prominent place in history.
Hubble originally was sold as this instrument that was going to revolutionize our understanding of the universe, and it delivered on that promise, I think, more than anybody could have dreamed.
And all this has been possible because of the scientists and engineers who turned humanity's dream of a space telescope into reality.
In the dark days of the mirror flaw, if you had told me that I'd be sitting here after Hubble's 25th anniversary of successful observations, I would have said you're crazy. The commitment to find a way to fix it is one of the great things I've ever done in my life.
The lessons learned transcend engineering and science.
We tried something hard, it's important, and we screwed up. And it was such a screw up that the whole world laughed at us. But the important thing in that story is perseverance. We kept trying, and we eventually succeeded.
And that's a story that we humans love, and it's certainly one that I loved having been a part of.
They told us we couldn't possibly succeed.
At the end of the 1960s, NASA starts work on its most daring planetary mission, placing 2 spacecraft on Mars to search for life.
To say that that was an easy process would be a huge mistake.
Project Viking will challenge engineers to the extreme. Not to build big, but to build small.
You're talking about a biological laboratory, and you're shrinking it down to a box 1 foot on each side.
Well, who are we kidding? It would never work.
I'd say it almost brought us to our knees.
To succeed requires a spacecraft that must work by itself millions of kilometers from Earth.
And if any of that goes wrong, it's game over.
As mankind plans a return to the Red Planet, this is the story of the unsung heroes challenged to make the first successful landing on Mars. July the 20th, 1976. The Jet Propulsion Laboratory, California. Project manager Jim Martin and his team of engineers are on the verge of making history by safely landing the Viking spacecraft on Mars.
638, okay.
Over 300 kilometers above the surface, Viking 1 begins its critical descent.
Flag deploy. Confirm Roma, over.
And this must have been one of the most anxious experiences one can imagine.
59,000 feet, to be close to mortar fire.
Every engineering device must work perfectly.
Your heat shield has to come off at the right moment. Your parachute has to deploy at the right moment.
Lander confirmed parachute deploy. 1, TM2.
And then that blast descent coming down to the surface.
Parachute separation. 177 feet per second.
We were at a critical stage.
Suddenly, Jim Martin's phone rings.
Jim got a call from President Ford.
The president's on the line, and he wants an update.
Good roll, attitude, hold.
He told him he couldn't talk to him now. He was too busy. And he hung up on him.
After 7 years of planning, all Jim Martin and his team can do
73 feet per second. Come on.
is hope Viking makes it safely to the surface. The story of Project Viking begins in the 1960s. With the success of its first manned moon landing, NASA starts planning an ambitious planetary mission. The destination, Mars. Although smaller and further from the Sun than the Earth, our neighboring planet has some startling similarities.
It has seasons like the Earth. Its day is roughly 24 hours long like the Earth. It even has ice caps like the Earth.
The planet's likeness to ours is so strong, NASA designs Project Viking with one goal in mind.
One of the overarching questions in all of science is there life outside the Earth? And that's the unique thing about Viking. Viking was a science-driven mission.
At over 300 million kilometers away, the search for life on Mars will test engineers to the extreme.
To think we could do this was an absurd assumption.
We knew nothing about Mars at the scale of a lander, or nothing about what it was really like on the surface.
We didn't know whether Viking would sink in the dust. We didn't know whether it would hit a mountain.
During the 1960s, one reason Mars remains enigmatic is the challenge in reaching it. The Soviets and Americans launched numerous missions, many ending in disaster.
Mars is much tougher because it's so much farther away. You have to be incredibly precise. The targeting, the navigation through millions of miles of space.
For Gus Gustafaro, Viking's deputy project manager, it's a journey full of unknowns.
Therefore, we were going to write a spec that had a lot of TBDs in it. And we're going to have to get these TBDs answered. And you know what TBD is? It's to be determined.
The best way to search for life on Mars is to land there. How to do that safely is one of the engineers' biggest challenges. They must choose one of two options.
Option A was to send a lander directly to the planet and have it land without going into orbit first.
It's called direct entry. On arriving at Mars, a flyby module releases the lander, which descends straight to a predetermined location.
You don't go into orbit first, you just come screaming in and you slow down, you get to the surface. So with direct entry, you're gambling big time. You're just coming in and hoping for the best.
The alternative, option B, involves an orbiter that carries the lander. On arrival, they both go into orbit around Mars. The lander then separates and descends to the surface. It's called the out-of-orbit mode. For Viking design manager Norm Krabel, option B has one big advantage.
If you do out of orbit, you establish an orbit and take advantage of that and do some reconnaissance and decide, can I go in where I wanted to, or do I have to go someplace else?
There's no better redundancy than reconnaissance before the attack.
Option B plays it safe with an orbiter, but adds an extra $70 million to NASA's most expensive planetary mission to date. At the end of the 60s, fighting the Vietnam War means America's debt is spiraling. An expensive mission to Mars is hardly a vote winner. Congress slashes NASA's budget, making the cheaper option A the obvious choice.
It was, in fact, quite surprising to many of the people involved in Viking that NASA chose option B over option A.
What's more, the agency requires engineers to build a second, identical spacecraft, Viking 2, as a backup.
And the rationale is that projects like Viking are rare. And when you do them, you should do them right.
To pay for it, NASA must spread the enormous cost over more years, delaying the launch to Mars from 1973 to 75. For mission designers like Gentry Lee, it's a godsend.
After we first started the Viking project, Jim Martin and all the rest of us knew that we had bitten off more than we could chew. But we didn't really want to go to Congress or to the president and say, I don't think we're going to get there by 1973.
Viking's complexity means every second will be needed to design and build the spacecraft. Searching for life on Mars will stretch those involved to the breaking point. Spring 1970. Engineers on Project Viking start the challenge of constructing America's first spacecraft to land on Mars. At the Smithsonian's National Air and Space Museum, it's possible to see the finished lander, designed to search for life on the red planet.
So as you can see, the lander is quite large. It weighs about half a ton, and it carries a pretty robust instrument package. It has a high-gain antenna for sending signals directly back to Earth. It also has 2 cameras that scan the landscape, and probably most importantly, a biological experimental package for analyzing soil samples.
If life exists on Mars, scientists expect it to be found in the soil. But that begs an all-important question.
How do you look for life on another planet when you have no idea what that life is like? You start with the assumption that at some basic level it's going to be similar to life on Earth.
On Earth, the simplest life forms are microscopic organisms. They're also the most abundant. Viking will search for similar microbes in Martian soil by looking for traces of gas produced as they live and breathe. To do this, the landers will carry 3 life-stimulating experiments. A lamp will warm Martian soil in the hope any organisms will react to light. Another adds varying mixtures of water and nutrients, encouraging microbes to exhale. The third adds drops of liquid nutrient, nicknamed chicken soup, coaxing any microbes to feed and metabolize. If Martian life exists, Viking will hopefully detect any gases the microbes produce, proving their existence in the soil. But engineering these experiments is a phenomenal challenge.
You're talking about a biological laboratory, something that would take up a significant amount of space in a scientist's lab. And you're shrinking it down to a box that's 1 foot on each side, a foot cube.
Restricted by size and weight, engineering Viking's biological experiments requires miniaturization on an unprecedented scale.
And the thing is jammed with, valves and pipes and miniature ovens and Geiger counters. It's diabolical to even think of trying to do that and doing it on a timetable.
1972. With 3 years till launch, keeping Viking on schedule is the job of Jim Martin.
Jim was an extraordinarily demanding project manager. Nothing short of excellence was good enough for Jim.
Jim runs a military-style operation, devising a notorious strategy to deal with the challenges.
And his concept was a top 10 problem list. And so top 10 problem list became very much a part of the culture of Viking. Sometimes the top 10 list had 11 items on it. And I mean, it was almost depressing as to how challenging some of these things were.
And the biology experiments were on that list for a very long time.
Incredibly, 40,000 parts are crammed into a space not much bigger than a briefcase.
I'm sure the engineers were tearing their hair out.
I'd say it almost brought us to our knees.
But the task is about to get harder still. Combating an invisible threat, biological contamination.
In order to prevent any terrestrial bacteria from going along on the trip, the lander had to be sterilized before it was put on the launch vehicle and sent to Mars.
Earth microbes can create a false reading and wreck the biological experiments. Worse still, they can contaminate Mars, irreversibly changing the planet. To sterilize the half-ton lander, Deputy Project Manager Gus Gustafaro turns to a profession that kills microbes for a living.
We looked at the medical practice, how they sterilize the equipment they have that might touch the human body. Why not use the same thing on electronic parts and materials that we're taking to the planet?
During construction, both spacecraft are repeatedly disinfected with antimicrobial fluids. But to be certain they're sterile, the team makes a radical decision to copy another hospital procedure.
And so we stole from them the idea of baking our whole spacecraft in a big oven.
Each lander is cocooned in a bioshell and placed in a 9-meter oven where nitrogen gas, heated to around 115 degrees Celsius, bakes them for almost 2 days.
I mean, you can imagine these engineers, okay? They've got to design things that have never been built before. And now somebody comes along and says, oh, by the way, everything you build has to withstand this baking in an oven of 240 degrees for 40 hours. And they must have just said, you got to be kidding me.
Think about putting your camera or iPad in your oven and turning up the temperature and leaving it sit there for a few days. That's what we did with the lander. We couldn't think of any other way that guaranteed that we weren't taking any Earth life to Mars.
Over 5 years, every element of the spacecraft is designed and tested, hopefully ironing out each engineering pitfall. Now, with Viking built, it's time to put the engineering to the test. Summer 1975. Viking 1 and 2 will be launched on twin Titan rockets. The responsibility falls to Andy Stofan.
I launched rockets for NASA for 20 years. It's a strange job because it either blows up in your face or it's 100% successful. There's no in between.
Placing the spacecraft on a precise trajectory to Mars means both rockets must launch within a narrow time frame.
I was well aware of the importance of the Viking mission, so anything that went wrong with the vehicle would then lessen the probability of getting the two Vikings off.
August the 20th, Viking 1 gets away on time. But technical problems delay Viking 2 to the last possible launch day, September the 9th. Then something even the engineers can't control threatens to intervene.
The weather became marginal from a safety point of view as to worry getting struck by lightning either on the pad or during the launch.
Project manager Jim Martin consults local meteorologists and makes a call. Stop the countdown and wait for their predicted lull in the storm. With just hours of the launch window remaining, it's an incredible gamble. Thankfully, the weatherman's anticipated gap in the clouds passes right over the Cape. Viking 2 is launched with less than 5 minutes to spare.
To the great sigh of relief of myself and the Viking, the spacecraft people who were sitting there biting their nails.
The Vikings are on their way. Now the team must wait almost a year to get a shot at making history, attempting the first successful landing on Mars. June the 19th, 1976. A defining day for the engineers. Viking 1 arrives safely in Martian orbit. At over 300 million kilometers, sending communications takes around 20 minutes each way. So when the lander makes its rapid descent, it must be able to think for itself.
To do that was a whole new engineering challenge of creating an electronic brain that could carry out all of those things on board.
In the 1970s, computer code is typically stored on plastic tape. But sterilizing Viking at over 100 degrees Celsius creates a burning issue.
Had we heated the spacecraft that much, magnetic material would have melted away along with the tape in the storage system.
Engineers require a radical rethink. Viking sequencing expert Milton Holt thinks there's a solution.
And it looked like, hey, this is the way to go.
It's a metal storage device designed for the military. It's called pleated wire memory.
So on these strands of wire were the instructions that would get the lander to do everything it had to do.
It can withstand the sterilization, and it shouldn't be too difficult to manufacture, as we thought at that time.
In fact, engineers face a painstakingly intricate task.
It took 3,000 wires laid up by hand, and the intersection of each of these wires had to be totally in place within the width of less than a human hair.
This was like some kind of old world handcrafted creation, this very precise work. You could not afford to screw that up.
the finished computer contains all the information needed to land Viking on Mars, with a memory 100,000 times smaller than today's desktop computers.
This is going to sound unbelievable today, but that computer had 18,000 words of memory, and they sweated blood to get every one of them on there.
July 1976. Now in orbit, Viking 1 uses its cameras to give the team their first detailed view of its pre-selected landing site.
And the first pictures were alarming, and I really mean alarming.
The landing sites were chosen from pictures taken almost 5 years earlier, when the Mariner 9 spacecraft orbited Mars.
The Viking orbiter pictures were a factor of 10 better in resolution, and the change was just astonishing.
What appears smooth in the Mariner images now looks decidedly dangerous.
There were features that looked like giant fingernails had scraped across the surface.
There were huge boulders, trash bin-sized boulders, that could potentially kill the spacecraft if it landed there.
I mean, this was not the place that you wanted to throw a $500 million worth of lander at.
But luckily, the original decision to orbit Mars rather than head straight to the surface buys time to search for a safer site.
But they still had some time pressure on them. Viking 2 was on its way, and also the nation was watching.
As the new pictures would come in, the scientists would look at them closely and try to figure out, you know, based on counting craters, how rough is the surface likely to be in that spot.
To say that that was an easy process would be a huge mistake, because it just took meeting after meeting after meeting.
First site, rejected. Second site, rejected. We rejected the fourth one, rejected the fifth one. It's now July the 10th or so, and the second Viking is about to get to Mars, and we can't manage two of them at once.
After 22 intense meetings, Gentry Lee and his exhausted team make the final decision.
3 o'clock in the morning, we're looking at the pictures of the sixth site, maybe it was the seventh, I forgot which one, and finally Hal Mazursky, who was one of the most eloquent spokespersons for exploration of the planets, put his head down on the table and said, "This is probably as good as we're going to find, and I'm tired." And so with that, we decided we would go down.
20th, 1976. With the landing site chosen, it's time to make the descent. After final checks, the critical go command is sent. And Viking 1 is released from its orbiter.
Separation. Descent sequencing, we're mission eventward.
I will never forget the moment that I first realized all the intelligence that we had or did not have had to be inside that computer, on board that lander, heading for Mars.
That separation, you know, it's lost its mother, so to speak. It's by itself. It has to get there through a sequence of events that are pre-programmed.
For the next 3 hours, Viking is completely dependent on its onboard computer to safely reach the surface.
And there was almost a palpable sigh in the room. And almost as one, everyone looked at his or her watch and started mentally counting down 3 hours, so forth.
So, apprehension, yeah, I think there's a lot of apprehension.
To successfully land, Viking's key components must each work perfectly, starting with the heat shield.
You're screaming in at thousands of miles an hour, and you hit this very thin atmosphere, but you hit it at very high speed. It's got to be able to withstand that intense heat of that deceleration.
Next, still traveling faster than the speed of sound, Viking must deploy a giant 16-meter parachute.
So for the first time, we've got a supersonic parachute, which is a whole design challenge in itself.
A challenge Paul Seamers wrestled with during Viking's development.
The first thing we did with the parachute to qualify for Viking's flight was we put a model of it in the wind tunnel, and we had a big surprise. And that surprise was the parachute got torn to shreds. This turned out to be one of the worst days of my career, because I had to phone home to Langley and tell them I had just failed a parachute.
Paul's team discovers that at supersonic speeds, turbulent air behind the lander is too violent for the chute to survive. The failure means instant promotion onto Viking manager Jim Martin's infamous top 10 list.
We made the top of the top 10 problem list. How about that one?
Paul and the team must find a solution. They realize that by unfurling the parachute further from the lander, it experiences less destructive turbulence and remains in one piece. Now, back on Mars, the parachute works flawlessly, decelerating Viking to around 200 kilometers an hour. But a safe landing depends on overcoming one final challenge. Designing Viking 5 years earlier, engineers decide to use 3 retro rockets, slowing the lander to around 8 kilometers an hour at touchdown. But they discover a major flaw.
The tests were basically catastrophic. The propulsion system created so much disturbance, it would have compromised the science.
If there was any life there, the heating was such it would cook it, literally, kill it. So we couldn't detect it if it was there.
For engineers, it's back to the drawing board. Instead of 3 large retro rockets with damaging exhaust, they replace them with a cluster of smaller ones, with exhaust plumes that won't cook the Martian surface.
It resembled a shower head. There were 18 nozzles on each engine, and that solved that problem.
Parachute separation.
But has it worked? Have the years of engineering toil finally placed Viking 1 safely on the surface of Mars? For everyone on the team, the moment of truth is about to arrive.
73 feet per second. ACS is close to vertical. Come on.
Jim Martin and the team at the Jet Propulsion Laboratory count down the minutes to hear if Viking 1 has landed safely on Mars. Intern Andrew Chaikin witnesses the drama unfolding.
And, you know, we were waiting and waiting and waiting because those radio signals were still en route in that 20-minute delay from Mars to the Earth.
It's like waiting for the bride to come down the aisle.
ACS is green, 1.5 degrees per second max, 0.2 Gs.
Finally, after 20 agonizing minutes.
Touchdown, we have touchdown.
It was almost so fast that you couldn't take it all in.
We have a touchdown time of 12 hours, 12 minutes, 0.7 second.
And everyone started clapping, and a great sigh of relief. And it was just elation through the whole room.
7 years to the day after America lands men on the moon, engineers successfully place the first spacecraft on Mars.
My father, he was born in 1896, before the airplane and the automobile were invented. And he's here, excuse me for choking up, seeing his son enjoy landing a spacecraft on another planet. It was just remarkable. I would have given up all the money I ever made for that moment.
I think people just had to take a short time to breathe in and out, that we had actually made it.
They were passing out champagne and and I had my first and only drink of champagne.
It's hard to state the feeling. I mean, it's a feeling of combined relief and excitement.
Job very well done. I'm assuming that we must be sitting right on the X. So everybody just did fabulous and couldn't be more pleased. Thank you.
But there's little time to celebrate, as everyone eagerly awaits Viking's first picture from the surface.
The anticipation of the first image coming back from Mars was extraordinary. I recall sitting glued to the screen in front of me.
With its unique cameras, it's hoped Viking will finally reveal Mars as never before.
It wasn't like a TV camera that would take the whole scene at once. It would take the scene line by line with a mirror that nodded up and down, and you would build up from left to right the entire scene.
And so we waited. And here's the picture in front of us. And on the left-hand side of the screen, down starts coming pixels.
And all of a sudden, 5 lines of picture came racing down from top to bottom. Just 5 lines, like that.
Here it comes. Yep, that's it. That's it. Oh.
But then a few seconds later, another 5 lines.
Oh, more. You rocks. Oh. That's beautiful.
And then another 5 lines.
And by the time it got to the footpad, you could see the rivets. And I remember screaming, "Look at those bleeping rivets!"
Oh. Oh.
You could see them clearly.
It's incredible to see that Mars is really there.
You know, we're taking pictures on the surface of Mars. Nobody's ever done that before.
There was not a dry eye in the house. All of us just burst with joy because every single person on that team had lived in fear that what we were trying to do was beyond human capability.
The damn thing worked.
We were there, we did it, and now the science can begin.
With Viking 1 safely on Mars, what could be the most profound experiment in human history can start. The lander will gather soil to examine it for life, using its sampling arm.
At the end of the arm, there's a scoop. Once the arm has collected a sample, it can then be retracted and turned to deposit that sample into the biological experiment package.
The onboard computer commands the sample arm to unfurl. But with the engineers and the world's press eagerly waiting, there's a problem. The scoop fails to extend.
Oh my gosh, it was a panic time. After all the glory of landing safely would still not be a success if we couldn't get any material.
If we couldn't get a soil sample, that would mean that lander was out of business.
There was a lot of apprehension because we didn't know why at first it hadn't moved.
The engineers are dumbfounded. With the Viking 1 mission in jeopardy, everyone is scrambling to understand what's gone wrong.
And that was when this young engineer came in and he looked at me and he said, "I just went over the sequence. Did you have a separate sequence to unlock the key?" "Oh," I said, and I remember that distinctly. I said, "That's it! That's it!"
The team can't quite believe it. A locking pin on the sampling arm's protective shroud has failed to drop free, and the arm is stuck.
Anytime we were testing on the Earth, we never had the locking key in, so we didn't have a sequence that removed the locking key first.
Incredibly, engineers have overlooked a vital part of the computer code that helps remove the pin. The solution is to write and then transmit the missing code to the lander. But with 1970s technology, That's easier said than done.
Well, the problem was the way you generated a computer program was you had a deck of cards and there were holes punched in these cards, and the position of the holes would tell you what command to load into the computer.
Working around the clock, the punch card code must be meticulously checked.
You'd be in there early morning, 2 or 3 o'clock in the morning, you'd put your deck in the computer, and it rejected. So then you got to go through this stack of cards and try to figure out, why did it reject this thing? Where did I make an error?
Milton and the team iron out every last glitch. Check the code works on Earth. And then it's radioed over 300 million kilometers to the lander. Now, they must wait.
The next day, when we got the pictures back, lo and behold, the pin was laying on the surface of Mars. And so we knew that this problem was behind us.
But Gentry Lee is not quite off the hook yet.
So I got to explain all this to the media. And of course, Jim said, now, don't embarrass yourself by saying you just forgot to unlock the thing. So I made up a perfectly honest story that made it sound much more complicated. I said, these instruments on Mars are very complex, and you have to study the sequences very carefully. And we found that we had made a slight error in the sequence. That was true.
We have touchdown.
Less than 2 weeks later, Viking 2 also makes it safely to the surface. Both landers sample Martian soil in their onboard labs. What they find remains one of the most contentious results in planetary exploration. The Viking cameras give scientists their first close-up look at the surface of Mars. But now all eyes are on the results of the biological experiments to see if they will detect microbes living in the soil.
There were 3 experiments. 2 of the experiments gave results that were not consistent with life.
That leaves one last experiment: adding nutrients to coax any Martian microbes to feed. What's detected comes as a shock.
The 3rd experiment, called the labeled release experiment, gave results that in 1976 indicated there was life on Mars.
But this positive result is controversial. On analyzing the soil further, Viking is unable to find any organic material, the stuff that life is made of, creating a dilemma. If there's life on Mars, where is the organic material?
One newspaper would say, Viking found life. Another one would say, Viking did not find life. And as a result, everybody was confused.
To confirm life, the science community requires more robust evidence, as planetary scientist Jim Green knows.
If each and every one of those instruments gave us a positive indication that a reaction could occur that was biological, that they were measuring, then we could be assured that it was life.
But Viking provides ambiguous results.
Now that means the scientific community couldn't get behind the idea that life exists on Mars today.
Even now, the Viking results are hotly debated, and the question remains: does life exist on Mars?
Well, we want to find that out.
Beginning in 1997, NASA returns to the Red Planet with a series of rovers. Studying the environment, their results have added to the speculation Mars might be able to support microbial life.
So now we want to go back and we want to attack it in a different way.
At the Jet Propulsion Laboratory, the latest generation of engineers, like Matthew Robinson, are designing a bold new mission with a twist.
We want to return the samples back to Earth so that we can process those samples with instruments that have much more precision and much more capability than what you can send to Mars.
NASA plans to bring back to Earth Martian soil and rock samples to analyze for evidence of both present and past life. Helping design the vehicle that's going to select the samples is Mars rover veteran Rob Manning.
Now we're building a new rover to land in 2020. However, it does something that no other rover has done before.
It has the capability of drilling rock, creating about a chalk-sized sample full of a history of Mars. This is an enormous engineering challenge.
Matthew and the team are experimenting how to extract a sample.
The way that we acquire samples is using a coring bit, much like a drill that you would get from a hardware store.
The drill will be able to extract core samples from soft sandstone to the toughest granite.
Once we core into a rock, the robotic arm moves up and it goes over to the rover.
This core sample will then be very carefully put in a container that will then be left on the surface of Mars, along with many other core samples, which will later be collected by a future mission that will bring those cores back to Earth.
And that means a whole new generation of engineers are going to tackle this problem now. But they have one major advantage. They have the knowledge that has been given to them by the Viking engineers, demonstrating how we can do this.
It's a lasting testament to the Viking team that their technical achievements, made almost half a century ago, allow missions to land on Mars today.
It's amazing and mind-boggling that they were able to pull that off at such an early time in human engineering history.
It's like a symphony in many ways, and each of these individuals played their part.
All I could think of was, and I hugged the people around me, we did it! We did it!
We did the impossible. This is a symbol. This is my Mars 76 buckle. It was the biggest thing I've ever been involved with. And it worked, like I expected.
I have to confess, I've got a real feeling of pride of having been a part of it. And the emotional feeling's still there. That's everything I know, more than I know.